Hello all, myself Jen Popat. Let us understand permeability and seepage numericals today. In previous three videos, we have understood different theories and formulas of this chapter. Let us practice some numericals now. Let us start with problem number 1. Determine the average coefficient of permeability in horizontal and vertical directions for a deposit consisting of three layers of thickness having size thickness 5 meter, 1 meter and 2.5 meter respectively. The coefficient of permeability are 3 into 10 raised to minus 2 mm per second, 3 into 10 raised to minus 5 mm per second and 4 into 10 raised to minus 2 mm per second. Let us solve this by writing given data first. Here Z1, Z2 and Z3 as well as K1, K2, K3 are given. Z1 will be 5 meter, Z2 1 meter and Z3 2.5 meter. Same way K1 permeability 1 3 into 10 raised to minus 2 mm per second. Second 3 into 10 raised to minus 5 mm per second and third 4 into 10 raised to minus 2 mm per second. Now for calculation of KH and KB we have the formulas but you have to remember those formulas. So formula for KH horizontal permeability will be K1Z1 plus K2Z2 up to KNZN upon total Z total depth. Now putting all the values from given data we can find out KH as 0.294 mm per second. And same way we have Kv formula as Z upon K1 by Z1 plus K2 by Z2 up to Kn by Zn. Now Z total Z, that is total depth, that is 8.5 and other values are given for individual cases. Putting all the values in the formula we can have answer Kb as 2.53 into 10 raised to minus 4 mm per second. Again, if you remember one thing, always KH will be greater than KV for the same soil. Here, you can also observe that KH is greater than KV. So let us move to second problem. A soil sample of height 60 mm and cross-sectional area of 100 cm square was subjected to falling head permeability test in a time interval of 6 minutes. So height is given, cross-sectional area is given, so we can find out volume, then falling head is done in a time interval of 6 minutes. So T, small t is given, the head dropped from 60 cm to 35 cm. And if the cross-sectional area of standpipe is 2 cm square, then compute the coefficient of permeability of soil sample. And if the soil sample is subjected to a constant head of 20 cm, calculate total quantity of water will be collected for flowing through that sample. So problem is quite easy. First we have to assume that is a falling head test and then we will go to another things. For falling head test, these things are given. L, length 60 mm, that is 6 cm. A, area 100 cm square is given. T given as 6 minutes, so 360 seconds. H1 and H2 60 and 35. Cross sectional area of standpipe is given as 2 cm square and H, that is head, is given as 20 cm. So let us find out according to falling head permeability test K. So 2.3 small a into capital L upon capital A into T log 10 base H1 by H2. So we have almost all the values. Putting it in the equation, I am getting K as 1.79 into 10 raised to minus 4 centimeter per second. Now you got K, but still it is asked that find out quantity of water. For quantity of water, I'll use this equation for constant head permeability test. Here I am using one simple statement, that is permeability of any soil should be stay same if you are using a one formula or another formula. So K I have got that and other values I have been provided with. So Q is also unknown, and finding out Q from here, Q is 1.79 into 10 raised to minus 4. So that is how we can find out quantity of water which is collected after flowing. That's it for problem 2. Let us move forward. In a falling head permeability test, the head causing flow was initially 50 cm and it drops 2 cm in 5 minutes. So initially it was 50 cm, then it drops 2 cm, so it became 48 cm in 5 minutes. How much time is required for the head to fall 25 cm? So it is quite easy. Case 1 is to be told as H1, that is 50 cm, H2 is 48. T1 is given as 5 minutes, so we can say 60 into 5, that is 300 seconds. Case 2, in which we want 25 centimeter fall. So H1 is 50 centimeter and H2 became 25 centimeter, and we want to find out T2. So we can compare very simple equation from K1 will be same as K2, as this is the same soil. And here I am using 2.3 AL upon AT log 10 base H1 by H2. Here, area of standpipe will be same, length of sample will be same, and cross-sectional area of sample will also be same. So, I can write out 1 by T1 log 10 base H1 by H2 for both these cases. Putting values of H1, H2 in case 1 from this side and case 2 this side, I'll get T2 as unknown, and T2 will be 5093 seconds, and we can convert it into hours and minutes. That is this. Let us move to next problem. Calculate the value of the coefficient of permeability of a soil with the effective diameter of 0.15 mm. So here permeability for an effective diameter is to be found out. Now effective diameter is given as 0.15 mm. Here effective diameter means D10. So D10 is given. So we have to remember the very beginning of this chapter and factors affecting permeability. There we have studied technical relations between different factors. There we have studied effective diameter and coefficient of permeability relationship. That is D10, that is 0.015 centimeter. K is equal to C into D10 square, where C should be taken from 100 to 150, but it is generally taken as 125. And D10 is given, so I can find out K easily, and putting C as 125 and D10 as 0.015, K value is coming out as 0.0281 centimeter per second. So that's it for this problem. These type of problem can be asked in exams for smaller problems. Problem number 5. A stratum consists of fine sand of 2 meter thickness. Now 2 meter thickness is provided and the soil type is fine sand. Under what head of water flowing in an upward direction will a quicksand condition develop? Take G and E as given. Here, quicksand condition is to be asked. What is quicksand condition? Let us quickly understand, revise that. Quicksand condition is nothing but when the effective pressure gets zero and the soil starts moving upwards or the soil particles are uplifted, then the condition is sand boiling or quicksand condition. So for quicksand condition, I must be equal to IC. I is hydraulic gradient and IC is critical hydraulic gradient. When hydraulic gradient becomes critical hydraulic gradient, quicksand condition will occur. Here I can be written as H by L or Z, and IC can be written as G minus 1 upon 1 plus E. Here H by Z is to be found out and G and E are provided, so Z is also provided here as 2 meter, right, thickness. So putting all values of G and Z, I am getting H as 2.08 meter. Now what does it mean? It means if the head water is gone up to this head, this height 2.08 meter, then the sand will start boiling or quicksand condition will start occurring. So you should take care of that on the field. Let us move to problem next. Problem 6. A soil has the coefficient of permeability of 4.75 into 10 raised to minus 2 mm per second at 30 degrees Celsius. Now determine its value at 27 degrees Celsius. So at some temperature, at one temperature, the K value is given as 4.75 into 10 raised to minus 2 mm per second. And finding out, it is to be found out that at 27 degrees, what will be the K? Take coefficient of viscosity at 30 degrees and 27 as 8 and 8.5 millipoise respectively. Now, what is viscosity and what is coefficient of viscosity? So, viscosity, let us quickly recall that viscosity is resistance to flow. So, we have discussed that if the permeability is very low, viscosity must be very high, or vice versa, if viscosity is very low, resistance is very low, permeability will be higher. So it is inversely proportional to each other. Now let us see and write given data first. So K30 and K27. K30 is given, K27 is to be found out. Eta 30 is given, eta 27 is also given. So we can write down K is proportional to 1 upon eta. Now K1 by K2 proportional to eta 2 by eta 1 can also be written. So I have written the similar thing. K27 by K30 is proportional to eta 30 by eta 27. So it is inverse. Putting values of all three provided and keeping K27 as subject and unknown of the equation, I am getting K27 as 4.47 10 raised to minus 2 mm per second. Let us move to next numerical problem 7. The construction of a flow net for a dam gave NF 8 and ND 20. The head of water lost during the seepage was 5 meter. So we have a flow net. From that, NF is given as 8, ND is given as 20, and the head of water lost during seepage was 5 meter. So head loss is also given. If K is equal to 3 into 10 raised to minus 4 centimeter per second, estimate the seepage loss per day per meter length of the dam. So basically we want seepage loss. We understood in the applications of flow net, seepage loss can be found out. While let us write given data. NF 8, ND 20, K 3 into 10 raised to minus 4 centimeter per second, and H is equal to 5 meter. Now it is quite simple to find out seepage loss. We have studied the formula Q is equal to K into NF by ND into H, where NF by ND was termed as shape factor. Sometimes in problems, shape factor is also provided. Now putting K, NF, ND and H values, I am getting Q as 6 into 10 raised to minus 6 meter cube per second, but I want it per day per meter length of the dam. So I am converting it into per day per meter. So Q comes out as 0.5184 meter cube per day. So that's it in this chapter, permeability and seepage. We will learn more GE in next videos. Thank you.